All right, shall we begin this exciting new video for today? It is Saturday afternoon, around 2 o'clock. I thank you for checking us out and hanging out with us on Twitch. I really appreciate you sticking with us and watching this journey unfold. For as crazy it is and has been, for as weird as I am and all over the place. So I really do appreciate that. It's been a lot of fun. It's been a learning experience for me. I've been having fun sharing information and teaching and showing what to do, what not to do, and it's been a good ride so far. It's been pretty fun. To my YouTube viewers, when you catch this video on YouTube, I definitely appreciate you sticking with the series so far. This makes currently episode 51, which is quite a haul. Still quite a bit more to do to this, to the project, to the board testing, before we're even close to releasing it. We're still trying to finalize all the basic subsystems tests and validate that they operate correctly. So right now we are working on trying to get the temp sensor, just to make sure we're getting valid data from it. I don't have everything I need to fully test it in depth, but we can get a pretty good rough approximation. I have a few pieces of equipment that we can use. So if you like what we're doing, definitely like and subscribe on YouTube. Hit that bell notification to be informed of future videos when we drop them. And let's get to it. So let's go over to the webcam real quick to show you where we are. So I've got another piece of equipment that I'll be using to help kind of test and validate. It's a little contactless IR thermometer. Basically just reads the temperature of the surface or whatever the laser beam's pointing at, roughly. So we'll just kind of use this to kind of rough gauge, rough shot everything. And then for reference, I have this guy. I still need to find my stupid thermocouple adapter probe for this guy. So I can actually use thermocouples. I got to figure out what I did with it. I might just have to order a couple more from Amazon. I'll find it. That way we can actually stick thermocouples to the board. Hopefully I'll have it before we start doing the deep tests. So internally it's got its own temperature sensor. And since it's less exposed to the external air, internals are going to be a little bit cooler. So it's reading roughly 20.8 degrees Celsius. And the PCB is reading approximately 22 degrees Celsius at the temperature sensor. Now, this isn't calibrated. I also have to make sure I log it into the test log that we're using this. Because it is going to be considered a piece of test equipment. So I kind of poked around with the code a little bit just to make sure I understood what we were doing. So we have the test log that we're still working with. Let's go ahead and update this. Helps if I make model 42520 serial number, and I remember seeing the serial number in the battery dot box where the battery goes. We just might as well log this. It is 9002511. Close up the battery box. Again, this is a piece of test equipment that probably could be calibrated, should be calibrated. But for what we're trying to do, it is fine. We just want to see if we're in the ballpark. And I know I haven't been pushing the latest changes and updates to get it. Like, it kept slipping in my mind, and I'll work on getting that updated. That way, this current log sheet will be updated. So we're trying to do the temperature sensor. Again, we're not going to be able to really get perfection off of it because without having all the right gear to measure, but we'll get close enough. So I am reading an ADC value. It's kind of bouncing a little bit all over the place, but that's expected with signal noise and stuff. So we would probably want to do like a rolling average of this data before we do the actual conversion of the, or, you know, before we settle on what the temperature actually is, just to account for noise. Because in retrospect, let's bring up in KiCad here real quick just to give you an idea. Come on, open this PCB. All right. So the temperature sensor is all the way up here, and it comes down. Yeah, I keep forgetting. All right. So where are you at? Right here. So right here. So it has to come all the way from up there to that corner of the ESP32. Now it doesn't seem like a lot, but electrically this is quite a haul. This is quite a haul for an analog data signal. And we might kind of have it routed around a few things that could be introducing some noise. The biggest thing you want to avoid on any board when you're routing signal cables is avoid switching power supplies. Always avoid switching power supplies with signal cables because they will interject noise. So I'm pretty confident those guys aren't injecting any signal noise into it. We could take steps to clean up the noise if we really wanted to. We could maybe throw together an op-amp circuit to put on the board to help clean up the noise. But we don't need to measure absolutes for this. We just need a general idea of how warm things are getting, like in an enclosure, to determine the fan. That's all we're looking for. We just want a good general idea. That's the whole purpose of that. That way, we can kick the fan on, maybe control the speed, ramp it up to help keep this guy cool. Because this is going to be the problem child right here. This guy is going to be generating the heat, and we want to keep it cool and comfortable. And that's the purpose of this. We don't have to measure absolutes. We are just looking for enough of a difference, enough of a change to drive this guy. So that's all we're doing. It doesn't matter. So we are getting ADC values. It's kind of hovering around, kind of ping-ponging between these values. I just switched over to the one-shot driver. I know I want to try to do this stuff on screen as much as possible, but there's so much to cover. And this code will be in there, and I had to make sure I understood what I was doing and all that. And there are functions in here to convert, and I have to spend really a lot more time to do the conversions. But since this is not the most important aspect of this build, I'd rather focus on the inputs and putting together the PLC stuff. Just getting this basically tested, make sure it is somewhat functional, is more than enough for what we're trying to accomplish right now. So let's take what we know, and let me bring up the data sheet. So I'm going to bring up the data sheet. So it's a PDF, and we have the TMP 36 version. So again, it tells us at 25 degrees Celsius, it puts out 750 millivolts. And that's great. So what we're going to need to do then is TMP 36. We're just kind of taking some notes here. TMP 36, negative 40. C to 125 C, and it outputs at 25. So that's perfect. So now we have that. Now what we need to do is Okay. So the factor is, so we have a 10 millivolt per 1 degree Celsius. That is the scale it uses. So we're pretty, it's pretty linear. So for every 1 degree Celsius it goes up, it's going to go up 10 millivolts. So at 26 degrees C, it should be 760 millivolts. And at 24, it should be 740 millivolts. So right now we are looking to convert this. And so I think I need to get in there and reset all my values and understand what my reference voltage is. Because if I'm not mistaken, it's not 3.3 for the ESP32. So I'm going to have to look over the data sheet a little bit more. Well, I need to understand its reference voltage, because that's really going to affect the yeah. So we're going to have to read through the data sheet and understand that what its voltage rating is, the technical reference manual, as they call it. So we'll have to definitely understand that. It should be here in the attenuation. And you see a 10. Yeah, we'll have to kind of Google that. So 80SP32, 80C. 12 voltage reference. Okay, 10, 12. So its maximum voltage is 2.45 volts. So 2,450 millivolts. So that is one of the reasons. So a lot of the ADCs built into these chips, they're extremely limited. They're extremely limited. And a lot of them have these weird thresholds and things like that where you have to do some weird stretching to get the voltage. We could use an op-amp to an op-amp circuit to normalize it, to kind of bring the voltage range down and kind of, bring it down by like a factor of bring it down by a factor so it's within the voltage range that the ADC can measure, and then have to do some kung fu in the firmware to basically scale it appropriately. Like given that information, so yeah, so that's pulled from the data sheet. So let's go here. ADC at dB is range, which is good because really cold we almost don't care about. We're so 150 millivolt we don't really care about. We just want to kind of like look up. So 750 millivolts. So let's see here. And I'm going to butcher this all up here. So if we're at the full scale, 2450 millivolts, if we divide that by There's no way that thing's going to be reading. Well, let's actually try something else. 2450 millivolts minus the 750 reference that we know there. Maybe go at 10. Oh yeah, so that'd be like 170 degrees Celsius on top of. So there's no way we're going to reach maximum output. So what I need to do then is go back to conversion. So there's a calculation to convert, and I'm just rough-shotting this, so forgive me just because I just want to just kind of see. So let's say, yeah, it's going to be noise. That's why we should be like using a rolling average and convert all this. So let's say 725 is the ADC value times ADC reference. Okay, VREF. According to the data sheet, VREF is approximately 1.1. And then let's calculate that back. Divided by 2 to the 12th. All right, so that's approximately reading 1.1947 volts, which is not right. It's 194 millivolts, which should not be right for the temperature, with about approximately 22 degrees Celsius. So maybe I've got something wrong. Let's go to 720. Maybe it's supposed to be the maximum analog value that we can read, which is 2450. No, there's no way. No, no. Oh, that's why I screwed that up. Because I didn't convert that to millivolts. So 725 times 1100. There we go. That makes more sense. Divided by 2 to the 12th power. No, it's still 194 millivolts, which is completely wrong. So I think I have something in here messed up. Okay. 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 You know, I've also not really run it through. Okay, there's another possible failure too. Is I never really added a bypass capacitor of 100 nanofarads to the ADC input pin to help clean up the noise. That's one of the mitigating factors we could have. Yeah, so I have to run it through calibration and stuff. And that's something we'll have to figure out how to do in our code. Well, let's see if we can figure this mess out. Go to definition. Okay, so there's the calibration routine. All right, so what we might have to do is throw in. I don't really care if there's any kind of not calibrated. Okay. I don't care about returning any of this. So let's see if we can throw in. When do we need to? I think we throw in calibration like around here. All right. So let's unit ID ADC unit 2. 2. And ADC bit with. Oop. All right. So that should do that. Handle. Grab this because it. Because it wants that. So let's grab this. All right. Let's see if we can clean this up. Let's see if it explodes and pukes all over us real quick. All right, let's see what she does here. Still bouncing all over the place. All right, so we're still bouncing all over the place. What I think it is I'm not using the right calculations for this. Let's see here. AC1 raw voltage. Okay. All right, so let's try. Let's throw this in here. ADC Cali handle. Handle. I think it's just handle. I think that's what it is. ADC raw voltage. All right, let's do that. Voltage. Give her that second new line. Voltage. Let's see what she does. Let's see if she pukes all over our faces. Okay. All right. Oh, percent deep, I think. Nope. Oh. Let's try this. Now let's see if that pukes all over my guts. No, it's just you. Helps if I spell things right. The struggle is real for me. The struggle is real. Please. There. Not puking anymore. Let's let it see if it can do the conversion internally for me. Maybe I'm doing something wrong. Because basically, the driver's got its own internal converter. Alright, so apparently it's not. Or I'm having it do something completely wrong here. Alright. Cali handle. ADC1 Cali handle. Well, I'm doing something wrong here. No. Maybe. Maybe I'm pulling the wrong data for it to convert. Let's try that. Oh. 736 millivolts. Okay, now we're getting somewhere. I think I was doing the math somewhere wrong. 738. So 750, that would be, let's just say 700, that would be 24 degrees Celsius. All right. So with the laser thermometer, we're getting 22 degrees Celsius. Again, I think we'd have to do a rolling average on this. Take the voltage, do a rolling average of the voltage values, and then get a result off of that, the converted voltage values. So 22 degrees C. And that's according to the infrared contactless thermometer that I have. And it's 21.3 according to the multimeter. Let's go here. So 22 degrees Celsius. So we need to go down, let's see, 3 degrees would be 30 millivolts. All right, so 25. Is equals, and then so 3 10 millivolts equals 30 millivolts. So we should end up with around 720 millivolts. Should be the approximate value. And with all the slop, again, a rolling average. So we do hit 720 there. I should have put a noise filter on that. I should have put a 10 nano. I should know better. That would have been the best way of the first most effective way is putting a 10 nanofarad or 100 nanofarad cap on the temp sense line. Let's see. Can I do that? I probably can. I have to find my through hole caps. I think I have 100 nanofarad. We could always skywire that in for testing if necessary. Again, this isn't like super important. We do have a range, and if we do a rolling average, we can clean it up. Temp sense is right there. We'd have to a cap between that and ground, which you could tagged 15. So 100 nanofarad cap right here, 0.1 microfarad between these two pins would clean that up a little bit. Do I have, let's see if I have one readily available in my parts bins right here that I keep. Again, I need to do some more super organization. And I do have a 0.1 microfarad. And I will constantly repeat my claims that 100 nanofarad caps you will run through like water. They are some of the most popular values you will ever find in any design. So, so what I probably end up doing is having to bridge. Yeah. So I'd have to probably do some fancy kung fu. Might actually be able to bridge it like this. I could actually make that work. That would definitely clean up the signal. Question is that super important right at this minute? The next thing we should check for is, so let's go back to here. So we are seeing within that range, again, rolling value, things to mitigate noise. So I'm going to do a very unscientific thing, and I'm going to just cover the thing with my finger. And we should see the value go up. So we are going up. Very unscientific. Now, we're going to do something even crazier. Ugh. I mean, the main thing is we're registering change. That's the biggest thing. I think what we'll need to do is kind of rework. So I'm heat gun set to the lowest temperature, and this thing probably still sounds like a something dying. So yes, still sounds like something dying. I apologize. I think it's time to replace it. Yeah. All right. That thing I don't think is safe. I think it's time to buy a new one and get rid of this guy. Yeah, that sounded horrible. I haven't used it in a little while, and my cats have kindly dropped it off of the storage location I had it in. Yeah, so it's probably not a very good thing to allow cats into your workshop. So take my word for it. Don't. They are probably one of the most dangerous creatures you could ever allow into your workshop because they like to play with everything. So what I will do is I use the hot air gun, the hot air rework gun. We won't crank it up too high because at the lowest temperature setting, it's still like around 100 degrees Celsius. Yeah. Oh, yeah. That's definitely going to put out more heat than I can. So what we want to do, keep that little booger up. Oh, yeah. Oh, yeah. Oh, yeah. We are registering change. It is registering temperature differences. Now we let it cool down. And she'll slowly cool down. So I say we do something crazy. Let me, while we let it cool down, I don't want to burn myself. Let's go ahead and rework that board. Get that webcam going. All right, let's just go ahead and put that temperature sensor on there. Or the resistor on there. Go to the webcam. There we go. Again, that's something I should have considered during the design phase. LED light on, get my soldering iron going. This is actually kind of one of the easier types of reworks because we're just bridging these two pins. All right. All right. Get some solder in here. Again, trying to do everything on camera, but my setup is a little bit difficult to get properly oriented. That might not actually be helping. So, what we're going to do, should not need too much flux or need flux at all for these pins. Generally, through parts like this are generally easy. I'll grab our tweezers. Oh, you little cheeky. You can hold on just long enough for me to get that pin bent into position. That's all I need to do. Let's see if I can get them pre-wired, pre-bent to about where they need to go. All right, let's try that again. Too much fun. Hello. Come on. You were on there before. Hey now. All right, fine. This game you want to play? Let's just use a little flux. Just play the game it wants to play. Hold the capacitor steady. This should help smooth out the ADC values. There we go. In the tip. Too rigid on that guy. Grab my towel. Inspect it under the perfect. Come on. There we go. Try to get that flux off there, the extra flux. But at the same time, not to accidentally pull our capacitor off of there. And yes, this type of rework is typical for a prototype phase, for a first spin of a board. So things do get missed. I've worked with plenty of other engineers on other projects, and they miss things. It doesn't matter how long you've been doing it, how much you've been doing it, things get missed. Sometimes you don't think about something, a data sheet doesn't quite tell you to do something, and you just don't think about it. So that happens. So we got that guy, so that should help filter out a little bit of the noise. Not the prettiest, but you know, it'll do a job. Okay, this guy back yet? Now let's see if it maintains any stability. We're still definitely going to need a rolling average for that. Still definitely going to need a rolling average. So if you go back to the main screen, yeah, we're still kind of oscillating around, just signal noise and other things. And I think we're waiting, what, around 2 seconds. Let's drop that. Yeah, build that. Let's kind of take a look. But actually using the internal voltage converter, it actually seems to be working. And it does read around room temperature. Yeah. So some oscillation. But that would be, so every 10 millivolt is a degree, right? So we're talking about a, you know, other than some of the weird anomalous numbers, which could just be extreme noise. Seems to be stabilizing a little bit more. There we go. A little cleaner, a little bit better. So one of the things we'll want to do is, and yes, you would definitely want to put the capacitor for the temp sensing line as close as possible to the ESP32, as opposed to as close as possible to the temp sensor. Yeah, so a rolling average, multiple samples before we kind of come up with, we'll keep within a voltage range. Because the data sheet does say, you know, we have, you know, it's plus or minus 2% accuracy over the temperature, and plus or minus half a degree for linearity. So we do have some, you know, allowance for that. So that's okay. So 720 millivolts, it's around some 40 millivolts. Let's see if the temperature is any higher. So it's still around 22. But I don't know how accurate the infrared thermometer is. So, but we'll take it. We saw temperature increase. We saw it drop. Let's put the heat gun on it again. We'll get more in depth with this as we develop actual code. But we've got some stuff to actually test the sensor, and that's the primary focus of what we were trying to do. It is reading. Again. There we go. That's all we wanted. That's all we asked for. It is changing with temperature. Cool, cool, cool. And we'll get better stuff because the deep testing will help us solve those problems. So at this point in the game, I would say that the win. Get this guy out of the way. We've accomplished that. Not perfect, not elegantly, but you know, it's what we're looking for. So I'd say the temperature sensor is operating properly. It's my code that's sloppy and needs fixed. So one of the things we want to do before we get too far ahead of ourselves. Again, all this is still in flux because we are going to be doing Rev 2. Let us grab, let's place a symbol. Let's see if it'll actually work. I might have to do it on my other computer, which is fine. Already placed. Yeah, I'm gonna have to do this from my other computer. I was just gonna go through the capacitor on there for the temp sense, but we'll deal with that later. I'll do that later. But one of the things we will do then is, let me go over here. Step controller. Is this what I'm looking for? All right. So, yes, that's correct. So what I'm gonna do is I'm just gonna kind of file, save a copy. Because it's gonna have to be a whole new ECR. I should rename the other one dash 01 dash 17 dash 26 dash 01. Everything's going to stay the same. All this is the same. Add now paired schematic, so I know what I'm. Hello. Oh. 10%. Round 2 to better filter out noise on the analog line. So we'll do that. Bench testing has a lot of on that line. Capacitor should help with it better. So, blah blah blah. Can be done, and we'll help. Operation of the device. We're going to prove it. We just have to do it. All right. All right. All right. So we have that ECN. Again, following all of our processes, QMS, logs, engineering change control log. Let's make sure we follow all of our stuff here. ECR number. Ah. ECN. Copy from that. Let's see. Need to copy the text, not the table. There we go. All right. There we go. Follow our proper processes. Much of a pain in the butt they are. Logged. Not two, but between. For better. Noise. Here we go. That sounds better. All right. Bam. All right. Again, I will accept that as a past test because we are seeing the temperature value increase. It does oscillate, but it's not a huge oscillation. And again, with a rolling average, we should be able to clean that up and have that nice and much smoother. Some variation is fine, considering its primary purpose is just to control the fan. So what I'm going to do is, just give me a second here. I'm going to at least turn this off, move the PCB out of the way for now, because I want to kind of at least roll in so I can show you on camera. Get that out of the way. I still have to clean my workshop. I have to organize and clean so much. So I'm going to show you what we're going to be working with next. So this is my board I set up to work with the Click PLC. I've got the discrete I/O module. I'm following, pretty much the industry color codes for everything. So with the electrical code, black and white are your mains. Red is also for mains, but typically used for if you've got a transformer in between. So like after a transformer, but black and white, your neutral, your hot, those would be for your mains. No matter how many phase, any hot phase would be black, any neutral would be white, and your grounds, your PE or physical earth, is either green or green with white or yellow stripe. Those are color codes, and I'll repeat it time and time again. Smack anybody who uses green or green, white, yellow for anything other than the physical earth grounds. Now, as far as your DC/signaling side goes, solid blue is typically used for your positive or your basic signaling. White with blue stripe. I've also seen blue with white stripe, but typically white with blue stripe would be your commons, your negatives, your return path. So I've got these two blocks broken up. This red one, red setup is my positive 24 volts, and the blue one is my negative, my ground, coming off the power supply. So it all kind of feeds into the PLC, and then the respective input and output blocks on the that go to the PLC. So we're going to be working on this. This is the Click Plus as defined. We will start this adventure tomorrow. This is going to be a little bit more of the struggle because we'll have the board over here. And yes, I have fancy wire away, all this. You can buy power supplies like this off of Amazon. Little breaker on the hot coming in from the one hand, just add a little extra protection for me and for the rest of the circuit. The DIN rail and all the connectors, all the terminal blocks you can get in kits off of Amazon. the wire wag off Amazon. The PLC and the discrete I/O module that goes into it, you can get off Automation Direct. I can send you links for all that. Again, I want to keep iterating and stating that I'm not getting kickbacks, sponsorship, or anything for any of this. So I just want to let you know. Obviously, the piece of wood I had is just like an old shelf that I had in one of my areas in the basement, cut down a little bit to make like a little PLC kind of holding and training area. So what we'll do is we'll pre-wire these guys for power and signals. So again, these are technically what they call inputs. So these would, be for like your buttons, limit switches, other controls, things like that. And these are outputs. So we'll tie these inputs to these outputs, and maybe we'll have a button kind of tied in here to tell it to go or something. Maybe a latching button or something. That way it starts the PLC program. It'll go through and sequence through the outputs, which will basically turn on these inputs, and we'll have the status flash because we'll be using the same input program that we wrote previously in code, the input test. So we'll be using that. That's why I wrote it the way I wrote it. Now we'll just have to tweak out the PLC program to operate it with it properly. And that'll satisfy the last test in here that I want to make sure works properly. Is we want to make sure we can use a PLC as a control source. Now, unfortunately, I don't have the PLC with the RS-45, because then we could kind of play around with like Modbus if we really wanted to, but that's beyond the scope of this, of our what we're trying to do right now. When we get down to writing the testing firmware to do some of the stuff, there's still a lot to do. There's still a ton of stuff to do, because this is just the subsystem test. The next set of tests are the deep system tests. That's where we could get some destructive testing. That's where we're going to current load the stepper driver. That's where we're going to current load, load the power supplies and check for ripple, make sure they can actually work. So we'll have the journey of building the test fixture for that with a very big power resistor. We'll build that together, and we'll get that to work. I have most of everything I need for it. I'll see about getting a fan to fit in the enclosure. We'll find a fan that'll fit in there. Pick up what I need off of Amazon if I need anything to do it. I have an idea of a fan I'm going to use. I can at least use to build it and prototype it, make sure it works. And then down the road, maybe replace the fan with a cheaper model, lower end basic model, because I've got an extra Noctua fan with PWM and TAC that I bought for another project I'm working on. And I could throw that in there just for testing, but I could just throw just a fan with just power, because the fan's just going to run just to keep that big resistor cool. That big power resistor, because when we start sinking current through that thing and it'll heat up fast. So we got a little bit of a road ahead of us to build that test fixture, and I think I'll just bring you along for the ride. That's the whole point of this video, is to show you what it takes, the steps, everything that's involved to do this type of stuff, to do it properly. It's more than just having an idea on a breadboard and you want to get a board out there. To do it right, there's a lot of stuff involved. Still have paperwork to catch up on, and we still need to clean up a lot of our test processes to meet our firmware, clean up our firmware, make it a little bit better. We can even take some of the tests we've already written and kind of clean them up, maybe automate them a little bit more. We could even try to roll it into a single test, but the whole point of this is to test each subsystem individually without interference from another subsystem. That way we can isolate and validate. So that's what we'll do in tomorrow's video, is start the PLC fun, the programming, and we'll go along for that ride. I'm no expert at PLCs. I'm learning them, and I'm trying to teach myself. and I think we can get the hang of it. The great thing about the Click series is the software is free, and they're really easy to learn, and they're low cost. I mean, relatively speaking. Again, don't spend money you don't have. Don't put yourself in a bind. I know how expensive things are. I have to pay bills too. So if you can't afford it, don't buy it. You don't have to follow along with everything I'm doing. But if you can and you want to learn more, push your knowledge, push your abilities further, I definitely encourage it. The Click PLC, you can, like I say, get up Automation Direct. I can throw links to it into the resource file, the markdown file that's in the projects with the projects. So I thank you for hanging out with me this afternoon, and I will look forward to getting together tomorrow and starting the PLC testing of this guy, getting the code together for that. So thank you, and have a great rest of your afternoon.